continuation of our previous session. We just move on from session 1 to session 2, where we'll be continuing about the GFET. In the last session, we have seen about the notations of an GFET, where in this GFET, we have already seen that it has three terminals, namely gate, drain, and source, of course, along with the channel. And we are seeing the channel can be used for both N-type and P-type. Hence, we have two types of your GFET. This continuation of the FET, we take only one type of a channel and see what is the construction and the working and the operation of that particular channel of a GFET. If one of the channel, namely N channel, is known, then obviously P channel can be analyzed easily. Hence, we see the operation of only one type of channel and we'll find the analogous of it so that we can learn about the P channel GFET also. One of the channel we can consider here is about the N channel GFET. Coming to the introduction part of N channel GFET, we know that a FET consists of the three terminals gate, source, and drain. The middle layer called as a channel, where this channel is responsible for the current to flow from the drain to source, or whether it is flowing into the channel or outside the channel, it is purely dependent on the type of the channel, whether it is N or the P. Considering only the N channel GFET, here it's just a FET whose channel is composed of primarily electrons as a charge carrier. It means that the majority carriers are the electrons, which acts as this majority carriers are the charge carriers. So, whenever the device is turned on, whenever the device is energized, then the charge carrier starts moving. When the charge carrier starts moving in the channel, then the current will flow. And the current will flow from one terminal to another terminal depending on the type of the voltage which is energized between these terminals. And when the energized is been there, when the voltage is been energized or when the voltage is been on, then the current is flowing from one terminal to another terminal. For example, if we apply a voltage from source to drain, and when source is at a higher potential than drain, then the current flows always from the source to drain because source is at a higher potential. Similarly, we can tell for the other terminals also. Okay, this operation of a N-channel GFET can be considered as types of cases, say like case 1, case 2, like that. Okay, before going into the operations of an FET, one should understand how the depletion layers are formed. This depletion layers is not a new terminology for you all because we have already seen about this in the previous module also. Okay, see, for this, let us suppose the voltage at the gate terminal, say VGG, is reversed biased, while the voltage between the drain to drain term, that is the VDD voltage, is not applied at all. Let this be considered as a case 1. Then, in this case 1, what happens is, observe carefully, when VGG is reverse biased and VDD is not applied at all, the depletion regions between P and N layers tend to expand. If this tends to expand, then this happens as a negative voltage applied. then instead of in a n channel, we say that the electrons are majority carriers. But when this negative voltage is applied, it attracts holes from the p layer towards the gate terminal. In this diagram, we see that negative voltage is being applied here between the gate and the source, whereas positive voltage is applied at the drain and the source terminal. That is, the source is of a lower potential than the drain. Hence, the source is negative, drain is positive. The voltage applied here is VDD. Between the gate terminal and the source terminal, VGG, we tell it is reverse biased. When VGG is reverse biased, we tell the gate terminal is of lower potential than the source terminal. If the gate potential is at a lower end, then here it happens like some negative voltage or 3 volts is applied. If that happens, then here this P type layer around the gate terminals, you can see here this P type around the gate terminals, here and here this gate terminals are connected together. The P type around the gate terminals attracts the holes. This happens only when as the negative voltage is applied, attracts the holes from where? From the P type layer towards the gate terminal, because the negative because the VGG is reverse biased. Coming to the other case, when VDD is applied, in the previous case VDD is not applied, means it's not energized at all. In next case, when VDD is applied means some voltage is being supplied at the drain. Then here we'll tell that when VDD is applied, positive terminal is the drain and the negative terminal is the source, because here the voltage at the drain has been applied. So voltage at the drain will be of a higher potential than the source. If voltage at the drain is at a higher potential, we tell that the current ID is flowing. What is the current ID means? It's a drain current. When VDD is applied, positive terminal to drain and negative terminal to source voltage, then to the drain, then we tell there is a flow of current. It means that the electrons will flow from source to drain, which we tell it is called as a drain current. This drain current is called as a ID. So we can see the difference between case 1, case 2. Look at the channel. Here it is broad and here it is narrow. This is because about the this is with respect to the voltage being applied between the drain and the source. So the supply here, what we tell here, the supply at the gate terminal makes the depletion layer grow. Supply at the gate terminal makes a depletion layer. See this shaded part is a depletion. Depletion layer. The supply at the gate terminal makes the depletion layer grow, and the voltage of the drain terminal allows the drain current from the source to drain terminal. Suppose we think at a point at some source terminal there is some other voltage, that is, suppose the point at source terminal is B and the point at source terminal is A. Then the resistance of this channel is such a way there will be a voltage drop as the terminal A, because terminal A is greater. It means like whenever whichever there is a higher potential than the lower potential, higher potential is named as, say, A terminal, lower potential terminal as B terminal, then the depletion layer expands. Depletion layer expands towards the positive terminal of the gate. JFETs have only one depletion mode of operation. As these layers grow, depletion layers grow, the cross section of the channel decreases, or the channel gap this decreases, and hence the drain current also decreases. When this drain current is further increased, as and when we increase, there is a point or a stage occurs where these depletion region, as I told you, the shaded part is the depletion region, that touch each other. If they touch each other, the depletion region around these P types, when they touch each other, then the path doesn't exist. It means that there is no way for the drain current to flow. When there is no path for the drain current to flow, then ID will be very, very, very negligible or very zero. Okay, it will be zero. Or literally we can say that the drain current is nil at this particular point. Hence we tell the point is called as the point at which it is called as the point at which these two depletion region touches each other, and that particular voltage where the applied voltage is being energized so that the depletion region is touching, that voltage is called as a pinch of voltage, represented as small p, or voltage V. V suffix P is a voltage called as a pinch of voltage. So I repeat, the voltage at which both these depletion layers literally touch is called as pinch of voltage Vp. The drain current is literally nil at this point, as we have already discussed just now. Hence, the drain current ID, I suffix t, is a function of reverse bias voltage at gate. Hence, gate voltage controls the drain current. So, we tell it as FET is called as a voltage control device, because the voltage which has been applied at the terminals controls the current, drain current. Hence, we tell it as voltage control device. Whereas in our BJT, we saw that it's a current controlled device. So, we are just proving here why FET is called as a voltage control device. Okay. So, here there can be a possibility of a question asking like why we say that voltage control device is called as an FET. Okay. So, FET is called as a voltage control device because the depletion region just touches, and that particular voltage where exactly the depletion region just touches each other and the path is being closed for the drain current to flow. When that is the drain current is exactly zero, then we tell that particular voltage as the pinch of voltage. And these voltage all, since the gate is a control terminal, so we tell is a FETC voltage control device. Next we just see that JFET, how it has been the variation of a JFET from the drain to source voltage also. Okay. Remember that JFET have only one type of or only one mode of depletion region. Okay. Now in this we see that here the VDD for the JFET, drain to source voltage variation, the drain voltage should be greater than 0. That is, VDD must be greater than 0 for current to flow in the direction defined in an N-channel JFET. When VDD is very small, the voltage variation in the channel will be obviously very, very small, because it will have no effect on the channel shape. So, for this case, the depletion region is only due to the PN junction PN junction as we see here in this diagram, yellow color in this figure. Okay, this is JFET, drain to source voltage variation. Further increase in VDD, tapered shape to the channel and increasing non-linearity in the drain current to the VDD is been seen here. See, there's a tapered shape. Then when the voltage is still applied, further applied, this blue color, whatever is the depletion, it just touches each other and it prevents the drain current to flow. That is, drain current will become 0. This process continues until this voltage VDS is reached, where the depletion region from the PN junction is merged, and this voltage, as we have already illustrated, is called as a pinch off voltage. This gives a relation between your drain to source voltage variation. Thank you.